The preparation of carboxylic acids have been discussed on our previous topics. Here are some of the examples. First is the oxidation of side chains of arenes. If you have an alkyl group here and you react with potassium permanganate followed by acidification, you will get benzoic acid. You can oxidize primary alcohols using potassium dichromate or chromium trioxide or potassium permanganate. You will get carboxylic acids. Nitriles can be hydrolyzed in acidic or basic conditions to form carboxylic acids. Aldehydes can be oxidized as well to carboxylic acids. Grignard reagents may react with carbon dioxide followed by acidification to form carboxylic acids. You can oxidize alkenes or alkynes via ozonolysis or potassium permanganate oxidation to get carboxylic acids. And recently, I discussed haloform reaction as a method to obtain carboxylic acids as well. The most common mechanism involving carboxylic acids and its derivatives is known as nucleophilic acyl addition-elimination reaction. This mechanism involves an initial attack of a nucleophile to the carbonyl carbon to form a tetrahedral intermediate. Next, your double bond is reformed and the bond to the leaving group is broken to form a new compound. This is essentially a substitution reaction. As such, it involves a leaving group. In our case, chlorides and carboxylate ions are good leaving groups. So, in nucleophilic acyl addition-elimination, the acyl chlorides and the acid anhydrides must be very reactive. Esters, carboxylic acids, and amides require protonation to produce good leaving groups. Because in essence, when the bonds to the carbonyl is broken, you will form strong bases. To convert them to weak bases or as good leaving groups, they need to be protonated. Aldehydes and ketones lack a good leaving group. Once these bonds are broken, you will produce very strong bases. Here is the relative reactivity of the acyl compounds. The acyl chloride is the most reactive because the chloride ion is a good leaving group. It's followed by the acyl anhydride, then the ester, then the amide. As a general rule, less reactive acyl compounds can be synthesized from more reactive ones. Acid chlorides can be made from carboxylic acids by reaction with thionyl chloride, phosphorus trichloride, or phosphorus pentachloride. Any carboxylic acid can be transformed to an acyl chloride very easily. After your acyl chloride is formed, they can now be used to react to nucleophiles such as carboxylate, alcohol, or amine to form other acid derivatives such as acid anhydride, ester, or amide. Acid chlorides react with carboxylic acids to form mixed or symmetrical anhydrides. A base such as pyridine is used. So essentially, you will need an acyl chloride or an acid chloride and react it with a carboxylic acid. This is pyridine, and you will form a mixed anhydride. Here, your oxygen will attack the carbonyl, and you will get a tetrahedral intermediate. The base, which is pyridine, can take this proton. This positive charge will disappear, the double bond will be reformed, and you will get a chloride ion, which will partner up with your cation formed from pyridine. Sodium carboxylates react readily with acyl chlorides to form acid anhydrides. Consequently, they can be used to react with nucleophiles such as alcohols or amines to form esters or amides. Cyclic anhydrides with 5 and 6 membered rings can be synthesized by heating the appropriate diacid. This is an appropriate diacid called phthalic acid. Heating this up will give you phthalic anhydride at 100% yield. This is a cyclic anhydride. On to esters. They can be prepared from acid chlorides or acid anhydrides with alcohols and a base, for example, pyridine or triethylamine. This is your acid anhydride, this is our nucleophile, and this is our base. The nucleophile will attack the carbonyl carbon. You will form your tetrahedral intermediate. Again, the base, triethylamine, will take this proton. The positive charge will disappear. The double bond will be reformed, and the acetate group will be cleaved. Thus, it will partner up with the cation formed from triethylamine, giving us our ester. Fischer esterification is an old method in making esters. Here, you need an acid, an alcohol, and a carboxylic acid. This is an equilibrium process and very sensitive to bulky groups. As an equilibrium reaction, any increase in the amounts of the reactants will favor the formation of the product. An increase in the amount of water, on the other hand, will favor the formation of the reactants. Gamma and delta hydroxy acids give cyclic esters, known as gamma or delta lactones respectively. These compounds easily form. We name them as gamma or delta based on the old system of identifying carbon locations. This is alpha because this is the carbon that is right next to the carboxyl group. Then followed by beta, gamma, and delta. And this oxygen attached to the delta carbon can attack as a nucleophile to this carbonyl carbon and form your cyclic compound. We call this a delta lactone. Lactones are cyclic esters. Amides are prepared from acid chlorides or acid anhydrides with excess ammonia, primary amine, or secondary amine. The amines need to be in excess because it needs to act as a nucleophile and a neutralizing agent for the acid that will be formed in this reaction. A cyclic anhydride and an amine followed by acidification yields a product with both amide and carboxylic acid. Here, you have your ammonia reacting to this cyclic anhydride and will get a carboxylic acid and an amide. Heating results in a cyclic imide. We call this cyclic imide phthalimide. A common method in making amides is the use of dicyclohexyl carbodiimide. DCC activates carboxylic acids to form amides with amines. This process essentially involves the formation of a good leaving group coming from carboxylic acid. To initiate this action, oxygen will attack this carbon, followed by proton exchange to get this compound. Then, this amine can attack the carbonyl group. You will get a double bond O here to form a dicyclohexylurea. This is a good leaving group. The product that is generated here is an amide. This is often used in linking amino acids together to form peptide bonds. There are other alternatives to dicyclohexyl carbodiimide that were developed, essentially just replacing these cyclohexyl groups to control their solubility with important solvents. Nitriles are formed by dehydration of the primary amide with phosphorus pentoxide, sinyl chloride, or boiling acetic anhydride. You can readily form your nitriles in this manner. Also, You can prepare nitriles by nucleophilic substitution of alkyl halides by the cyanide ion and through cyanohydrin formation from aldehydes or ketones. Acid chlorides and acid anhydrides readily hydrolyze to carboxylic acids, and this is a common precaution in handling these compounds. They should be kept away from moisture, otherwise they will degrade to carboxylic acids. So your anhydride, when it reacts to water, will readily form two molecules of carboxylic acid. One of the common reactions of an ester is with sodium hydroxide, leading to a sodium carboxylate and an alcohol in a process called saponification. This process is often used in the hydrolysis of fats and oils. In here, the hydroxide will attack the carbonyl carbon, and you will have this tetrahedral intermediate. The double bond will be reformed, and we will have a leaving group. If our leaving group is this alkoxy group, we will have an alkoxide and form the carboxylic acid. Now take note that the hydroxide can also be a leaving group because the basicity of the hydroxide and the alkoxy group are comparable. If your hydroxide is the leaving group, we will return back to the original. That's why this process is reversible. However, this is a base and this is an acid. This alkoxy group can take this proton rather easily and form the carboxylate and the alcohol. This process is irreversible because of the strong acidity and basicity of the reactants. Thus, overall, saponification is an irreversible process. Lactones can be hydrolyzed with aqueous base, also by saponification. Mixing of carboxylic acids and ammonia or amines yields ammonium salts in an acid-base reaction. This is an example involving benzoic acid and methylamine to form your benzoate and methylaminium ion. Take note that the pKa of benzoic acid is 4.2 and the pKa of your aminium ion is 10.64. This is the stronger acid, and essentially this is our stronger base. Thus, this reaction is favored. Heating an amide in concentrated aqueous acid or base causes hydrolysis. You will form a carboxylic acid and an amine. However, this process is very slow compared to ester hydrolysis. A nitrile forms carboxylic acid upon hydrolysis with aqueous acid or base with heating. I have discussed this already during the topic of aldehydes and ketones. Beta-ketocarboxylic acids and their salts decarboxylate readily when heated. The products are ketones. This reaction is favored because you form a gas. The reaction is pushed forward through Le Chatelier's principle. Here, this double bond takes this proton, and then a double bond to the carbon is formed here. This bond is broken to form your enol and the carbon dioxide. The enol readily tautomerizes to the ketone form. Similarly, if you use the carboxylate, it will readily form the carbon dioxide. This bond will break. You will form your enolate and the carbon dioxide. Acidification will give you the ketone. Esters react with two molar equivalents of a Grignard reagent to yield a tertiary alcohol. You can use any Grignard reagent, and when it reacts with an ester, you will generate an alcohol with two alkyl groups coming from the Grignard reagent. The Grignard reagent attacks the carbonyl carbon, and your ethoxide is the leaving group. The ethoxide as leaving group is favored in this case because the Grignard reagent is a stronger base compared to the ethoxide. That's the reason for its propensity as a leaving group. You will form here a ketone. This process cannot be stopped effectively at the ketone stage, and another molecule of Grignard reagent can attack the carbonyl carbon to form this alkoxide here. Acidification of this compound can give you the tertiary alcohol. Thus, two equivalents of your Grignard reagent is used in the process. You might be wondering why this reaction cannot be stopped. The reason for this is the effective positive charge at the carbonyl carbon. If you would compare this ketone and this ester, oxygen can donate effectively its electrons to the carbonyl carbon. Thus, the carbonyl carbon in this ester has a lower intensity of its positive charge compared to this carbonyl carbon in the ketone. Your Grignard reagent has a higher tendency of attacking the ketone in the presence of the ester. On to reduction. Lithium aluminum hydride reduces carboxylic acids, acid chlorides, acid anhydrides, and esters to alcohols. This is an example of an anhydride. Lithium aluminum hydride can convert this to two equivalents of an alcohol. This is an ester. Lithium aluminum hydride can convert this part into an alcohol to form this one. This bond will break to form your alcohol coming from the alkoxy group. Lithium aluminum hydride reduces amides to amines. Again, if you have an amide, you can readily generate your amine with lithium aluminum hydride. Borane reduces carboxylic acids to alcohols. Diisobutyl aluminum hydride is a specialty reagent. It is also called DIBA or DIBAL-H. It reduces esters and nitriles to aldehydes at low temperature. This is an ester. DIBAL-H can react with this ester to form an aldehyde. Take note that if you use lithium aluminum hydride, you will form an alcohol. The low temperature is required. If you use ambient temperature, DIBAL-H will react like lithium aluminum hydride. Sodium borohydride is not efficient in reducing esters, carboxylic acids, or amides. Acid chlorides become alcohols, however. If you react this compound with sodium borohydride, the ester is untouched. Only the ketone part becomes reduced. Metal-catalyzed hydrogenation does not readily reduce carboxylic acids, but it can reduce acid chlorides to aldehydes.